Hi everybody, it's Dr. Nigro with the Physics Fundamentals Screencast. This screencast is going to look at batteries. We're not going to go into a deep dive on what's inside of a battery. We're going to focus instead on what a battery does, how we can set it up in a circuit, all right, and what differentiates one battery from another. If you want a little bit more look at the inside of a battery, there are a lot of great resources online. I strongly recommend that you go check one of those out. All right, so let's start with the definition. All right, what is a battery? Well, a battery's job is to act as an energy storage device. All right, it stores energy, and when we need that energy, we put it into a circuit, and then it provides energy in the form of electron flow due to chemical reactions within the battery. All right, so it's chemical potential energy that's present within that battery. All right. Again, if you want to learn a little bit more about what that reaction, or not one reaction, there's actually two reactions, what those reactions look like, there's plenty of information about that online. All right, so a battery we know is cylindrical in shape for the most part. There are obviously other shapes. It's got a positive end, the positive terminal, and we call this the cathode. And then it's got a negative end, which we call the anode. All right. A chemical reaction occurs at each electrode within the battery. The cathode's job is to absorb the electrons as they re-enter the battery. And absorb's it's not the best word. The reaction utilizes those electrons as a reactant. On the anode side, the electrons are produced by a chemical reaction. All right, so the electrons basically run from the anode up and around to the cathode. So here are electrons flowing around. Now, you should never connect a battery like this. This is a very bad idea. This is just for an example, a little picture for you, all right, because there's nothing in between and the batteries are going to overheat and burn out. So don't do that. But that's the direction of electron flow, all right? Now, how do we designate batteries? We really talk about batteries in two ways. We talk about their size, and then we talk about their potential difference or their voltage. All right, size is pretty straightforward. We've got C val, we've got Ds, we've got double As, we've got triple As. All right, and these all are same voltage. All right, so if I hooked each one of these batteries up to a light bulb, then the light bulb would shine at the exact same brightness for each one because each provides the exact same potential difference. All right, remember, potential difference is defined as the push for an electron current. All right, it's the reason that the electrons flow in a particular direction. There's a positive end, that's the cathode of the battery, and a negative end, which is the anode of the battery. And the difference in charge between those two ends is what causes the electrons to start moving through our circuit. All right, so it doesn't really matter how big a battery is. If the voltage is the same, then they're going to be able to move the electrons in the same way. All right. Now, if it comes to voltage, all right, we have 1.5 volt batteries, which are what we're most familiar with, are double A's, triple A's, C's, and D's, all right? And there are also 9 volt batteries out there. Those are the ones that look like rectangles that have the two electrodes on the top, where one's positive and one's negative. There's also 12 volt batteries that you find in cars and boats, and then there's a whole multitude of other voltages out there, but these are the 3 that we see the most. All right, so when it comes to brightness, the ability to light up a light bulb, for example, or make an electronic run, all right, the 9 volt battery is going to be stronger than the 1.5 volt battery, and then the 12 volt will be even stronger than the 9 volt battery. All right, so basically, if you have more voltage, you have more electrical potential energy per coulomb of charge. All right, so that means that those electrons will have more energy with which to move through that circuit. And the more energy something has means that they can do more work. All right, and if the work is lighting up a light bulb, then they will be able to make that light bulb brighter as they go through it. All right, if you have wires at home and you have batteries, it's very easy to tape wires to two ends of a battery and then touch the two ends of a light bulb, and you can see it for yourself However, make sure that those wires are insulated, all right, so that those electrons flow along the path that you want. All right, so size, really, the only benefit you get from moving up to a bigger size battery is as it contains more chemicals, and if it contains more chemicals, it will last longer for you. All right, so if we need to run something that requires quite a bit of current, all right, then I'm going to go with a D cell battery so that I don't have to change it so often. If I need something that requires less, then I go with the AAA or AA, all right? So things like boom boxes or radios, I just dated myself, all right, they're going to require larger batteries because there's more components in there that need electrical current. Whereas your remote control for your television, small, not a whole lot needed in there, so you can go with a smaller battery. All right, regardless, you're going to get the same energy output for each battery as long as it's the same voltage. All right, now, what if you need more voltage, but you don't want to use a really big 9-volt battery? All right, what can we do? All right, well, we can set up combinations of batteries. All right, so combinations of batteries come in two forms. You can set them up in series, right? And when you set a battery up in series, you're doing positive to negative, and you repeat it. All right, so what that would look like, let me see if I can draw some. All right, so we see how we have a positive end and a negative end, positive and negative end, positive and negative. So we've got them end to end to end. And you can see this in most of your remotes. If you open them up, you can see them laid out in a line. All right, now if we ran a wire, and let's say it stops at a light bulb and then comes back, all right, the voltage that we're going to get here, and we'll assume these are just 1.5 volts each, is the sum of these voltage values. So it's going to be a lot brighter than a single 1.5 volt battery. And that's because it's additive as it goes down that series setup. All right, the pressure, the push that the potential difference can give increases as you add another battery in. All right, so the total voltage here is going to be the sum of the voltage values of each battery. So in this case, it would be equal to 4.5 volts. All right, and that's going to give you a brighter light bulb because those charges have more energy. If they have more energy, they can do more work. And if they can do more work, the light bulb will be brighter for us. All right, now the other option is parallel. All right, and so for parallel, it's going to be positive to positive, negative to negative. All right, so my students were like, well, why would you even do that? Because if a battery goes out in series, then it opens the circuit and the circuit stops. So it's all done. You have to replace everything in there. All right. That's why when you have batteries go out in your remotes, you don't know which one's out. You got to replace them both. All right. Parallel, if you lose one of your batteries, the circuit will still continue to work. All right. So there are some electronics you might want to set up with battery powered in parallel so that if one blows, you can keep using that particular setup. All right, now what does that look like? Let's see if I can draw one. All right, so here are my three. These are my 1.5 volts again. All right, this is my positive end. This is my negative end, and I would set it up like this, positive to positive. And let's say this is my light bulb, and then it comes back around, negative to negative. All right, so this would be a parallel setup, all right, where the negative ends are attached to the negatives, positive to positive. All right, so what does this really get us? All right, so the electrons are moving from the negative end to the positive end. So this electron, let's use this light blue, could choose to take this loop right here. All right, that would be fine. All right, let's say we have another electron come out of this one. It may decide to skip that loop and go here and then come back around. Or maybe we have a third option. Let's put him right here. And he comes out and he decides to go through the light bulb and then come back around. All right, so what the parallel setup gets you are branches for electron flow. All right, so you really can actually have a higher current in a parallel setup because you have more places for the electrons to go. Whereas in a series setup, there's only one path. There's one loop, one path. All right, so you're kind of stuck. All right, so there are benefits, pros and cons to both setups. Personally, I like the idea of the parallel setup because if one thing blows, the whole circuit doesn't go. But there are reasons to additively put in voltages. So, the series setup has its place as well. All right, so let's look at a couple questions. All right, so your teacher hands you three 9-volt batteries. Draw diagrams of the batteries in series, parallel, or a combination. All right, so we're going to start with series. All right, I'm going to draw these this way this time. All right, I'm not an artist, so you'll have to forgive my cylinders. They don't look that great, but all right, so this is positive, negative, positive, negative, positive. Whoop, well, I just did that one backwards. Oh no, I skipped a negative. That's what I did. Sorry about that. Oh, positive, negative, positive, negative. All right, so these are all connected. All right, so my wire is going to connect the negative end. We'll run it through, let's run it through a light bulb, and then it'll come back here. Okay, so our electron current will flow from negative to positive. All right, our conventional current will flow this way. All right, remember, conventional current looks at the motion of a positive charge, so it is always reversed from the electron current. All right, now, because this is in series, the total voltage is going to be the sum of all of our voltage values. So in this case, I've got a 9-volt battery, a 9-volt battery, and a 9-volt battery. I'm going to have a total of 27 volts. All right, so in other words, I have 27 joules of energy for every coulomb's worth of charge. All right, and those 27 joules of energy can be converted into work as they move through that light bulb. So the light bulb's going to be very, very bright. As a matter of fact, that's probably a little too much for the light bulb, and it might blow. But that's okay. This is pretend. This is for example. All right, so this is our series setup. All right, so now let's try a parallel one. All right, so positive, negative, positive, negative, positive, negative. All right, so we'll have a wire, go to that positive one, and then we'll have it loop through a light bulb. We'll have this, and then return. All right, so once again, the electrons here are going to have paths. All right, we could have one electron start here and go through the loop this way. All right, we could have a different electron start here and go through the loop here. And then we could have a third choice. We go through the light bulb and then we come back. All right, all of those different paths are available to the electrons. All right, now you might ask, well, how does the electron choose? All right, if the voltage values are the same, the resistance is the same, they will split equally among the three choices. If there's a path within the choices that has less resistance, the majority of the electrons will go there. All right, but you always will have electrons moving through each path. Just the partitioning of those electrons is going to depend on the resistance, which we haven't really gotten to yet in class, but we'll be talking about that soon. All right, now because these are in parallel, all right, the total voltage is just the voltage of each one. And since these are each 9-volt batteries, the total voltage is going to be 9 volts. All right, now one thing to keep in mind, if you're in parallel, all batteries must have same voltage. All right, that is not the case in series. You can put a combination of voltages together over there. But if you're in parallel, everything has to be the same. All right, so with that in mind, a combo of series and parallel is not possible. All right, if I put 2 of those batteries in series, that would give me a total of 18 for that portion. And if I tried to put those 18 volts in parallel with 9 volts, it's not going to work. All right, so there's no combo possible with these batteries. All right, now that's not to say you can't ever do it, but you just can't do it with this particular setup. Okay? All right, so let's slide down to this one. All right, this time the teacher hands us three 3-volt batteries and one 9-volt battery. List all the possible combinations and total voltages. All right, so I'm going to start with series. I'm not going to draw these. I'm just going to write them out. All right, so I could put them all together. All right, so put all of them in series. That's going to give me a total voltage of 18. All right, I also could drop a battery. So maybe I do 3 plus 9. So that'll be 15 volts. Or I could do 3 plus 9, which is 12 volts. Or I could do 3 plus 3, plus 3, and that's 9 volts. Or I could do 3 plus 3, which would be 6 volts. All right, so those are all my series combinations. All right, I could just have a single batteries. All right, if I do single batteries, I either have 3 volts or 9 volts. That seems pretty straightforward. All right, now parallel. All right, there's only one possible combo here. All right, I would need to put the three 3-volt batteries in series and then set that set in parallel to the 9-volt. All right, so in other words, my 3-volt batteries, right? And these are in series with each other, positive to negative. All right, and then in parallel is my 9-volt battery. All right, so over here, I have a voltage total of 9 volts, and then I put that 9 volts parallel with my 9-volt battery, so the V total for the parallel portion is 9 volts. All right, so that's really the only way I can do that and put things in parallel. If I remove one of the 3-volt batteries, then my series set will be 6 volts. That won't match up with the 9 volts, so I can't do it that way. I could put the 3-volt batteries in parallel, so I guess technically I shouldn't say that. There's two. I hadn't thought about that one. Two possible combos. This one or the 3-volt batteries in parallel. And I drop the 9-volt battery. And if I do that, then my total voltage for that is going to be 3 volts. Okay? All right, so when we're talking about batteries, we just need to keep in mind what their job is in a circuit, right? We need to think about what the size of the battery does for us versus what the voltage of the battery does for us. And then when we talk about combinations of batteries, we need to understand what it means by series versus parallel and how we calculate the total voltage that that setup can provide if it's in series or if it's in parallel. Okay?